The previous week, we reviewed what we learned before these semesters. First of all, about quantum mechanics. Quantum mechanics have starts from a particle wave dualities, and using these characteristics, we could uh, get a wave functions using a Schrodinger's equations, like here. That means that if we know that electrical potential energies, we can define a wave functions like here. And if we know electrical potentials, and we could a electrons movement like kinetic energies to relations between kinetic energies and these wave vectors. And there is another characteristic is the tunneling effect. Tunneling effect is that a wave meets the potential barriers. In classical physics, it could not happen through these barriers, but in quantum mechanics, if the width of the barriers is sufficiently narrow, then they can go through these barriers. And there is a band theory, which means if those silicons or semiconductors atoms get together, then there is a bands are formed, like here valence band and conduction band. In valence band, electrons are fully occupied at thermal equilibrium, which means a 0 Kelvin, and the conduction band, the electrons are fully empty at thermal equilibrium. So we could, using these Schrodinger's equations, we could find relationships between energies and wave vectors, because as silicons are too much, there are a lot of silicon atoms in crystals. We could move the domain into frequency domain. So there is a direct band gap and indirect band gap. And the difference between a direct band gap and indirect band gap is that in direct band gap, electrons can go jump up like here with just band gap energies, but the indirect band gap needs more than band gap energy. So we in intrinsic silicon atoms, by the mass actions law, the concentration of intrinsic semiconductors is like here, but we use these intrinsic semiconductors with doping, which means that we donate these more electrons like in n types, and we accept electrons in p types here. The density of state means that the available seats in the electrons here. The density of state means that how many states can exist in the EK diagram. So we could, by using a density of states and Fermi-Dirac distributions, which if a density of states means that a set to available states in the band. Fermi-Dirac means that a possibility to exist in the band. Here, at thermal equilibriums, there is no electrons in valence band, and the possibility is zero. At valence band, there is fully occupied, so possibility is 1. As the temperatures goes up and at electrons generate at conduction band and holes combine in valence band, there is a difference between them. So a concentration of intrinsic semiconductors is that state of the density of states times Fermi-Dirac distributions, and if we integrate by the energies, we can get a concentration of the carriers. Then the doped carriers have, like here, difference. The concentrations are different in carriers. In PN junctions, PN junctions means that junctions of p-type semiconductors and n-type semiconductors. At equilibrium states, there is a space charge and the depletion regions and the built-in barrier potential. We use these PN junctions giving them a bias, and at forward bias conditions, the built-in junction potentials gets low, so that they carriers inject from the other side of main carriers are injected from the other side, so that they can carry the moving electrons that can make the current. But however, in reverse bias means that giving the potentials by different side, there is a generation and recombinations by the thermal energies and the tunneling effect. So by calculating those sides in depletion regions using Poisson equations, we can learn that the width of the depletion regions are defined by a here like doping concentrations. So in electrical ways, we can get a equivalent circuits using here like resistors or capacitors. In depletion regions, there's small carriers. There's hardly to move the carriers, so it is hard to move the carriers between them. But in here and here, the energy level is almost the same, so they are equipotentials line, so that can move relatively easier than the depletion regions. And the capacitance is that by the charge neutrality, they are neutralized, but in the end of it, there is a charges so that they can act like a capacitance. So we can use this, calculate those capacitance by capacitance and voltage relationships, and if we square them and use 1 over c squared is that related to doping concentrations. So if we know a capacitance of the diode and the voltage, then we could get a doping concentration, or vice versa. And there is a metal contact semiconductors. We use it a Schottky diode, or in the p-n junctions end of it there is a metal contact. In metal contact, a work functions and there's metals work functions, and there is a semiconductors work functions, which is Fermi levels to vacuum level energy level. The difference between the built-in energy is that the difference between semiconductors work functions and metals work functions. The meaning, they in forward and reverse bias, they act similarly like p-n junctions, but they are absolutely different. In forward bias, the tangent line is very not sloped, but in reverse bias there is a very steep, so that then a tunnel effect can go through. So if we get a current voltage characteristic in metal semiconductor junctions, if we lightly dope them, then there is a difference between built-in work functions are different, act like semiconductors, but if we heavily dope it, then there is a MS junctions act like a ohmic device here.